Alicia, can you hear me all right? In the back? You can't hear me all right. And now can you hear me? Move it up? Okay, is this better?
Yeah.
Okay, if I get too loud, put your hands over your ears. Wow, okay, so here we are in the afternoon. Had a wonderful presentation this morning. You're well fed. If you feel sleepy, you won't offend me putting your head down or wandering around in the library or checking your email or something. That's completely fine. It's my great pleasure and honor to be here. First time in Texas. 6 months ago, I never would have thought I would have ever been here. But due to one of those international events and meeting Dr. Tashikori, Professor Tashikori, I was able to come. So I want to thank you. That's Farsi. That's the extent of my Farsi. Except that actually my Farsi is that. Okay. And this is a wonderfully organized conference, and certainly I want to thank everybody involved in that for doing that and making sure I got here and so forth. Okay, so I'm an emeritus professor, as you heard, which means an old fart. It also means that I'm not responsible for being a fool, because there is no fool like an old fool. And I want to try to present something today that may offend you. It may cause you to think that's just a toy, it's too silly, it's too stupid. Because I'm going to try to teach you a technique of doing statistics that's quite, I would say, radically different than what you've learned in a couple of ways. One of them is you can do it on your fingers. So you won't find it on SPSS menus. You won't find it. I wrote a few programs in R to do it, but you might as well just get out a piece of paper and do it. So that's different. It's also different because it tries to emphasize something I think is lacking, certainly in psychology, I know. That's the ability to analyze data from individuals and then to aggregate over the analyses, rather than to aggregate across individuals and then do analyses on the aggregates. And as you may well know, if you don't, I'll tell you now, you get different results from that. So I'll try to show that. Also, there's one occasion when I may ask you to sing along. So this will have a little musical interlude to it as well. Okay, so let's start out with warm-ups. Let me start out with a pre-warm-up. And someone once asked a bunch of scientists, what is science? And like most fundamental concepts, it's really hard to define. The one I like most, in part because part of my life is spent in the arts, is that science is art using numbers. And that there's not really much difference between really good artists, creative artists, and really good scientists. It's just that one of them uses paints or numbers, paints or words, and another one uses numbers. So you're going to get kind of an artistic slant on all of this. As you may know, in evolutionary biology, there are people called lumpers and people called splitters. People who like to make fine distinctions between different kinds of subspecies and so forth, and people who just say, it wiggles. So I'm more of a lumper, and I'll tell you a bit why, because I come from a mathematical modeling tradition, my discipline. And people who do modeling of that kind, not statistical modeling, but other kinds of modeling, don't really care too much about statistical significance and so forth. So I'll leave you with a bit of that. Okay, now for the warm-ups. Just two quotes. The first one is slightly sexist, but it was 1964. You may know John Platt. People in social psychology know him by a very famous article called Social Traps that came out, but he did lots of other things as well. Beware the man with one method or one instrument, either experimental or theoretical. This applies to women as well. What I'm going to make an argument is that that we are mostly in the social sciences using only one method, or one instrument, take a pick, and that is something called the GLM, the General Linear Model. And in my own unbiased fashion, true to the tradition of TARDIS, I'm going to say it's probably the worst thing that ever happened to the social sciences, and 100 years from now people will look back and say, my God, why did they make those mistakes? Another one comes from one of my old professors years ago who said something that really perked me up. We don't make intellectual progress by challenging conclusions. We make intellectual progress by challenging assumptions. So what I want to do as part of this talk is to challenge some assumptions. And then after trying to show some of the problems of these assumptions, address the question, so what? Or if you can't do anything better, shut up. So we'll try to put up. Speaking of one method, I guess I'll be generous and say something like this. If you look through research journals in the social sciences, certainly in psychology, you find out that despite the diversity of their topics, their methodologies, in particular their statistical methodologies, tend to be fairly uniform. And it goes something like this. 95% of all statistical analyses in social psychology use only 5% of available statistical procedures. If you go over to a statistics department, or if you read the statistical journals, you find out that every year, I don't know, somewhere around 500 new statistical procedures are invented. And most of them lie in obscurity. I've invented 2. And I couldn't tell you from my experience that I'm learning one today. And the ones that are chosen tend to be variants of this thing called the GLM, the General Linear Model. That's the one that has a lot of B's or betas in front of things and some plus signs and a little thing at the end called error. And I'll talk about some of the strengths and weaknesses. But there are variants of the General Linear Model, and in order to use it properly, you can always use it improperly too, but to use it properly, you have to rely on some normal parametric assumptions. These are parametric kinds of things, parameters being mean and standard deviation. You tend to look at the world as existing and functioning as a result of differences between means. So we focus on central tendency, which is, of course, only one aspect of distribution. And we tend to partition variance into epicyclic, we call it orthogonal components. You have this thing called the grand mean, and if you were using analysis of variance terms, there are these things called marginal means which circle around the grand mean, and then we have interactions that circle around the marginal means, and then we have higher order interactions that circle around the circle arounds that circle arounds that circle arounds. And you start thinking, wasn't there an astronomer that did something like that? Ptolemy, and he had this model of the solar system. And, that got junked, why don't we do it now? The other thing, of course, is in addition to partitioning variance, okay, then there's that other part. And we've heard eloquently about it, the Nyman-Pearson significance test or some variant thereof, which is basically concerned with issues or questions about whether or not your samples can generalize to some population. And what I'm going to try to argue is, by challenging substance, it was something that Margaret Foddy, one of my colleagues in sociology many years ago, pointed out when she started reading psychology journals. She said, what is it with you psychologists? You're always asking, can we generalize from the sample of the population? That's not an interesting or even important question. The important question in science is, can you generalize from your theory to your observations? And that's a very, very different question requiring very, very different statistics. Do people know a wonderful paper by Alan Newell called You Can't Play a Game of 20 Questions and Win? How many people have ever heard Alan Newell's or read? It's freely available on the internet. So if you write down Newell, 20 questions in Google, you can get it. I highly recommend it. As one of the early critiques on the null hypothesis test, where we basically say, Is it significantly different or not? Yes or no? Is it bigger than a bread box or smaller than a bread box? Again, it's the 20 questions game you may have played in a car many years ago. Basically arguing that that's not the way to do science. Okay, so given that there are potentially some problems with what we're doing, and we're overemphasizing one particular approach to statistics, one of the questions that we ask is why? And a typical answer, that I remember hearing quite a lot in my youth, was something like, well, almost all important questions can be answered with traditional statistical methods. That somehow it covers all of the really important things. And if you don't have a question that can be somehow translated into a statistical model, like the general linear model, then the question isn't worth asking. So, might as well ask, is that true? If it is, you can convince me, I'll stop talking, or I'll go home. I'm going to argue that it's not true. And if it's not true, what are the alternatives? So that's what we're going to try to get in for today. So, putting my cards on the table, here I stand, as Martin Luther once said. If the good old Mr. Venn, right, in his diagrams, and they're almost circular. There's no rectangular diagram. Okay, so if the brown represents important questions in psychology, and the green represents questions answerable by the general linear model, I think if you talk to traditional people in psychology, they have a kind of mental conception that looks like this. Well, yes, the important questions in psychology, except for a little tiny bit here, can all be answered by the general linear model. Maybe there are a few more, but that's for future generations to figure out. Right now, I got to publish. My opinion is that history will show more like this. That, yeah, there are some questions that are important that can be answered by the general linear model, at least in psychology or education psychology. But I think we'll start to discover that more and more of the really important questions can't be answered in that way. Have to be addressed in some other way. So, let me do my best I can. This is the weakest part of my presentation. Talk about what's good about the general linear model. One of them is it's mathematically elegant. Everything adds up. When I was learning statistics, we had to derive the formulas by hand. We didn't have SPSS, much less their menus. So it's really neat because you know everything adds up, and you get to undo these and get these estimators and so forth. And it's beautiful. It has its own linear beauty. Also, because it's a linear model, at least from a mathematical point of view, it's pretty easy to derive variations of it, which is one of the reasons why we have so many variations of it, and new ones coming out all the time. It's also very profitable. If you do an extension of the general linear model that does an omnivariate, multi-level, homoscedastic test on the residuals of the partitioning, blah, 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 and people want it, then you can add it to an SPS menu and you can sell it, which is one of the reasons why many statistical tests aren't on SPSS menus, because there's not enough demand for them. So you can extend it for research designs if the assumptions are met. And if you look at the history of SPSS, does anybody know about the company that makes SPSS? It's a vicious, shark-like company. It bought out all of its competition and then closed them down with a few exceptions. But if you look at it, you think, my God, when I used SPSS, before they had menus, we had to learn a little code and this, and then you got the menus, and there were about 6 different things on them, and then there were about 12 different things on them, and then there were about 25 different things on them. And pretty soon you think, in the future, 50 years from now, how many menu items will be on SPSS? You click one thing, this menu comes down, you have to scroll through it, figure out what it is. But it's convenient that way. So a lot of people who really don't know the inner workings of these models can be told, do that, and they click it, and because it's convenient, it's useful, and that's fine. people know how to use it. Okay? They know about the general linear model, that's what they're taught. They hated statistics, they breathed a sigh of relief when their last statistics course ended, and by God, they're not going to learn anything else new. That's too much of an intellectual challenge. And one of the consequences I've seen among an awful lot of people in my disciplines is that people, after they've gone through the indoctrination procedure, tend to look at the rest of the world and all the questions in terms of this way of thinking. We used to say, because I have some tradition of social psychology, that every time a social psychologist thought of an idea, the social psychologist would grab a piece of chalk, go up to a board, and make a square with a cross in it. You know, it's like, genuflected, you know, and then put male and female and old and young, and make some predictions that way. Thinking, the whole world acts that way as a 2x2 design. So, like the bed of Procrustes, you know, where people who were too short were stretched and people who were too long had their legs cut off so they could fit in Procrustes' bed. Sure enough, we tend to modify the way we think about the world. And yeah, there may be flaws with it, but it's like QWERTY keyboard. You know about the history of QWERTY. How many people don't know about the history of the QWERTY keyboard? Oh, good. Well, very quickly, back in the old days when typewriters were mechanical, and they set up the letters, they could be A, B, C, D, E, F, G, H, I, J, K, L, M, N, P. The most frequent letters is in the Dvorak keyboard in the center of the. When they made keyboards that way, people would very quickly learn to type really fast, faster than the machine can handle it. So you go boom, and then you have to take those little things because they're all stuck up. You have to use the mechanical and pull them back, and then you pull them back, so they're getting really frustrated. So some marketing genius said, I know, rather than trying to speed up the machines, let's try to slow down the people. And in order to do that, they took all of the letters and ran Bermuda. So people were P, or it's like the spelling of the English language. You know, like little kids spell English phonetically. Right? They say wrong, you're being logical. I'm sorry. And so, as my father said, there is a P in psychology, isn't there? Yes, it's silent like a P in swimming. Okay, what's bad about the general linear model? Click, click, click. Here are just a few things that I would sort of highlight. It requires, formally speaking, it requires data from a ratio scale of measurement because you're doing multiplication and division and you need a natural 0 point in addition to equal intervals and blah, blah, blah. I'm sure you've heard of that sort of thing. We rarely have that. Now, you'd think that if we rarely have it, we'd be concerned about it. And in the past, some people, about 3, were. But mostly now we think, it's close enough. I say, that's robust, or making up these kind of assumptions. And that's why, we have questionnaires. How many questionnaires are in the world that breathe at night? And they have these little rating scales. And it's like good, bad, like, dislike, and 7-point scales. And if you want to appear to be more scientific, you have 100-point scales. Or better. And then you realize that, and you get these numbers, and most people don't start to think, what's the nature of the distribution of those numbers? And what if it's not normal? And so forth. And it turns out that sometimes those have really important implications. If you don't believe that. How many people know about orthosonority? Have you ever heard the story of orthosonority? You know what S.S. Stevens, the psychometrician, very famous, had a couple of students who were trying to scale things like the loudness of tones and how it's related to decibels and that kind of thing. And a couple of the students started thinking, every time we do these studies, we come up with these data that look perfectly reliable. What do they mean? So they decided, let's invent a new dimension of sound. So they made it up. It was called orthosonority. And they would bring students into a laboratory and they said, we have discovered what we believe to be a new dimension of sound. Oh, yeah? Yeah. And we're going to ask you to to assess how much of this new dimension of sound there is. You probably have never heard of it. It's called orthosonority. You probably heard of pitch. Okay? You probably heard of timbre. You probably heard of a few other dimensions. But this is called orthosonority. Ooh, I've never heard of that. That's okay. I'm now going to play you a sound that's high in orthosonority. And now I'm going to play you a sound that's low in orthosonority. Now I'm going to have you listen to 100 sounds 10 times each. And for each one, I want you to rate how much orthosonority there is. Completely fabricated. So they do. They sit there, and that's another 7. It's like more like a 2. And they do all the scaling, and they get these beautiful curves that come out of meaningless material. And here's another way to try to do that. The next time you make out a questionnaire that has like, dislike, good, bad, those kinds of things, put one in there that says something like good, triangular, right? Or like, blue. And you'll get significant differences. So there are lots of problems with rating scales, and some of them are statistical. It focuses on differences in central tendency. Remember you took that stats course and they said, well, as you know, our big thing is called descriptive statistics. Well, we don't care about this. I'm going to tell you a few. Mean, mode, median, and they all start with M. Got that on their multiple choice exam. And really, the only one you have to know is the mean, because the mean is powerful. And the median is, the mode. That's for kids. That's for bar graphs. But everything, the mean. Yes, people act like this. Hi, I'm an average person. I'm the general mean. But someone told me I'm male. So I moved my average over this way. And then other people told me that I'm depressed. And that moves me this way. And my beta weights now say that, if I'm left-handed, but if I'm politically left-wing, you can just see the normal distributions of people going back, being pushed around like vectors and so forth. Now, maybe you can help me address this question. Have you ever had the course in statistics where they say, well, sometimes we have to worry about equality of variances, because if they're not equal, we lose power. What's this power thing? Concept I've ever heard. I was like, no, we don't want to lose power. Oh my God. Okay. So, test for equality of variance and pray to God it's insignificant. Phew, it's not significant. That's so that you can go after the means and see if they are significant. And you ask yourself, why don't I pray that the means are insignificant, but the variances are significantly different? That's because we don't talk about variance differences because they're a nuisance. I spent a year on sabbatical at Berkeley in the zoology department because I wanted to get out of psychology and figure out how other scientists thought about things. Zoologists, evolutionary biologists, and so forth don't think like we do. God bless them for that. One difference is this. They almost exclusively study differences in variance, not differences in averages. Okay? So, are these two species of fish have an average length that's different? I don't care. What I care about is that look at how variable that species is, and look at how homogeneous that species is. The zebra example, okay, is fascinating. You had a slide of zebras. Fascinates a lot of biologists because, look, they're the same. And why are they the same, or why are we so different? Right? What causes it? They're really interesting questions that can be asked about differences in variance. Partitions, variance, and Ptolemaic cycles and epicycles. I talked about that, how we have the grand mean, right? And then we have the main effect, right? And then we have that first order interaction goes around the main effect. And the second order interaction goes around. And we have this equation that that plots it out. And we think we've understood something. And in doing so, as we say in psychology, we substituted a statistical model for a psychological. And you might why do we do that and other disciplines don't? It's general and suitable for examining single cases. Hey, my mother just did this over the period of 17 years. Look at those data. I wonder if it's significantly changed. Well, I don't know, you don't have any error variance. Do I need error variance? Yes, you do, because it's the denominator of these equations, and if you don't have any error variance. So, add some error variance or something. Get another person so you can get some error. And have you ever thought, if you have perfect data, and everybody is exactly the same, doing exactly the same things and giving you exactly the same numbers, if you have no error variance, you're going to blow SPSS up because it can't compute. You're going to think, well, why are we using a model that can't compute when we have perfect data? And terrible problems, as you may know, collinearity, those kinds of things about analyzing correlated data, which is one of the reasons why very little is spent, at least when I was teaching statistics, on repeated measures designs. You have to make sure the data are all perfect, and you can't get people going off madly in all directions, or it screws up the analysis. So stop doing the research. It's called letting the statistical tail wag the conceptual dog. Limits of inference to on average, which are frequently not true in general. Do you realize that what's true on average is very often not true in general? Because I did a lot of research in decision making, and one of the things that we used to do is ask ourselves, what causes people to change their judgments and decisions? And I'll give you an example. If I say, what do you think of Stephen Harper on a scale from -3 to +3? You'll probably say, who's Stephen Harper? Good. You don't want to know. But if I tell Canadians, I say, who's Stephen Harper? And I say, well, he's the Conservative Prime Minister who's muzzled scientists in the last few years. Some people will say, then I hate him. And some people will say, then I like him. So on average, if you take those two groups of people and you average them, you get no change. But in general, information about Stephen Harper muzzling scientists has changed everybody's opinion. It's just that having one in one direction or having one in the other. So if you have a psychological model that says that this information changes people's opinions, it will not be proven or demonstrated on average, but it will be demonstrated in general. These kinds of things happen all the time in research and decision making. And the inference engine that's been grafted onto the Lyman Pearson kind of thing, grafted onto, seems to maybe be addressing, can I say the wrong question, or addressing only one or two important questions. In a way, if you look at other scientists, and take astronomers. Is astronomy a science? It actually used to be called natural history. That's another issue. But do astronomers, go out and say, oh my God, look at those stars. I think there's a straight line that can account for 70% of the variance of the movement of those stars. If you look at the Big Dipper, that's early pattern recognition. Do astronomers say, I got to do a t-test on that? Or do they say, I need a random sample of stars? Other ways to do some science. So you can do perfectly legitimate science probably by this way, but you can also do it another way. So not only asking or instead of asking. How we generalize samples to populations. Ask a more important question. Can we generalize from theories to observations? Which means we have to have a theory that generates some predictions, and we'll talk a bit about the difficulties of doing that. Although, how many people have a sociology background? Okay, is it still true that a required course in sociology is called theory construction?
We don't have theory construction here. We just study theories.
Yeah, it used to be a required, in psychology is the only discipline that there's only one requirement, at least in Canada, a course that's not psychology, and that's statistics. Yeah, you're in psychology, you got to take stats. Yeah, well, what about psychology? Oh, that's optional. When you go over to physics, they don't say, before you learn physics, you got to learn some stats. Anyway, in sociology, they used to have, it was mandatory that students took, for a PhD, a course called theory construction. What? They're textbooks on how to construct theories. Has anybody taken a course of theory construction here? Probably not. It's a legitimate area. Why don't we? Well, theories just come. They come in the middle of the night and they sleep under your pillow. What to do? We're about to sing, so. At this point, I have to quote Bill Lawson, one of my wonderful colleagues who is in the School of Business, and see if this applies to you. So, I've been thinking a lot about teaching in university. I remember my experiences. Before I went to university, I was ignorant. When I left university, I was confused. And sure enough, I was confused. Is there a solution to this? The answer is I don't know, but I'm going to show you one. You may like it. Okay, brief bit of history. When I was mini nerd, I was in training to be a dweeb. I used to be called, it was post-Sputnik era, and a lot of high schools had people called mathletes. Was anybody an athlete? They were athletes, but they had mathematics competitions. I lost every one. So I decided to go into math and physics, and I didn't do very well because a lot of kids had longer slide rules. And I went into music, and that'll come back to haunt me. And then I discovered this stuff in psychology, where you could actually write mathematical equations that would somehow describe or predict, or they thought, account for what people did. The simple ones were like Markov learning models. So I've heard about Markov chains and the little matrix with the transition probabilities inside, and you can say, oh, they're like I can know something or not know something, and then the next time you can either know something or not know something, and with a certain probability that you go from an unlearned state to a learned state, you make these predictions, and it's not the general linear model, it's more of a psychological model that tries to predict something, and then you ask yourself, so I got to get some data. Here's my data. Does it fit or not? And I'll tell you a little bit about the traditions for estimating fit in mathematical modeling land, which are similar to those in computer simulation. Incidentally, how many people know about what's called agent-based modeling? A couple of you. So where you write a little computer program that's kind of a cartoon caricature of a person. And then, so it gives you a little cartoon character of a person. Then you tell the computer, here's another kind of person. This is very typical, with different motives or different capacities to learn or different mobility or something like that. Now, computer, go make 100 of these and 100 of these and have them interact with each other and watch what happens. It's a very common way of exploring group dynamics and such, and I do a lot of that. So I come to this from a bit of a different perspective. So I did this mathematical modeling, and then I hung around with these evolutionary biologists, and here's another thing you find out in that area. In biology, they have these three different subgroups of people. They're people called theoreticians. They're basically mathematicians. There are people called experimentalists, and there are people called naturalists. With the hip waders who go out and find new species and name them after their supervisors. Why don't we have that in psychology? Why don't we have theoreticians and other kinds of people? And it was with the biologists I learned an awful lot about classification being really important, which we do almost none of in psychology, and other kinds of things like the variance differences and so forth. From hanging around biologists and computer scientists, and I was just a psychology reject, I learned the distinction between empiricists and rationalists. You know that, I hope. So empiricists are the ones who like to collect data. Is the moon far away? I don't know, let's see. Or why do children, when they come out of the womb, they're only about this big, and 25 years afterwards, they're bigger. Are you sure? Empiricists would want some data about that, the Francis Galton types. And then you get the rationalists, and they say, oh, actually, it's obvious. Can't we just, they're small when they're born, they get bigger. What are the implications of that? So Einstein was a classic rationalist, never ran an experiment in his life. Didn't publish much either. Remember that old New Yorker cartoon where they got Jesus on the cross, and you got two scholars down there. One of them looks at the other and says, yeah, he was a good teacher, but did he publish? And you may discover that one of the reasons why you might like statistics, if you do, but there's therapy for that, is that you're a rationalist and not an empiricist. And you happen to be in a discipline that values empiricism more. Other disciplines don't. Then there's a difference between the variance splitters and the goodness of fitters. Okay? These are the people who say, okay, I've got this model for it, and out come those beta weights and those equations and those little interacting components, and I cut up the variance and apply, I only got this much air, and my R squared, that kind of stuff. And then the goodness of fitters, of which I am one. Okay? And I'll show you how we, of the other persuasion, look at this. And then the difference between inferential versus evidential statistics. Now, I was taught that there are two kinds of statistics. They come in two flavors, strawberry and chocolate. No, it's descriptive and inferential. Huh? And the descriptive are little kids' things, and the inferential are really important stuff. What I wasn't taught is that there's a third group called evidential statistics. Sometimes they're known as goodness of fit tests or poorness of fit tests. So I started to learn these things and began to wonder, would psychology or any social science discipline benefit more from some other combination than the one that seems so popular here? And where did that lead? To give you an example of how it is that mathematical modelers, at least in psychology, try to assess the evidence for or against one of their models. Example. Suppose we have two models related to how people learn. One of them is shown in blue, that's model X, and one of them is shown in red, model Y. Those are the predictions they make about a certain set of data. And suppose the data, in green here, are plotted as well. Very typical kind of, here are predictions, here are observations. How close is the fit? In the 20th century, probably the best known and most respected mathematical psychologist was a man named William Estes, Bill Estes. Was at Stanford for most of his life. And I had the pleasure one time of, he visited University of British Columbia where I did my PhD. And he gave some talks. Okay? And he's a great mathematician. It's like Duncan Luce or all these luminaries. These equations, you can't fault him. So he does these kind of experiments, okay? And you think, wow, he's a mathematical psychologist. He's going to have a really sophisticated way of telling us which of those two models fits better. And here's what Bill Estes does after he shows you, if I can reproduce it. This tiny man. That doesn't look very good. Or if the prediction was red and we obtained blue, that's a bit better. But I'm a little worried about that right up there. So I got to modify mine. That's called the interocular trauma test. Also known, if it hits you between the eyes, you can trust it. If it doesn't, you don't trust it. It's using the old eyeball technique, which, as it turns out, you know what? All the stuff on subjective statistics, actually your eye is incredibly good, which is one of the reasons why a lot of people are looking for graphics. It's so much better than recognizing patterns than anything we've found so far. So why not let your eyes do the work rather than your SPSS menu line? But that's basically the way you do it. You don't ask, is that significantly different? Are the observations significantly different than the predictions? Oh God, no. You run in fear if you're a mathematical modeler. You think, oh my God, if I ran a statistical test, it will probably be significantly different, and that'll mean that my model isn't very good. So if I do run a statistical test, I pray that it's not significant. That's a weak way of saying, well, see, it wasn't statistically significant, so maybe it's worth looking at it. So people who don't like the in and out molecular common test and want a number to do it, try to invent evidential statistics. Statistics will tell us something about the comparisons of the observed versus predicted in model X and observed versus predicted in model Y. So in a way, you can look at these two numbers and see if they're different or not, if one is significantly better than the other. So that's the way we typically go about it, and that's the way I'm going to show you how to do it, but you can do it on your fingers, and you don't have to do any math at all, except count. Own and divide. Now, limits of mathematical modeling. Mathematical modeling is a very good way of doing science. Lots of other disciplines do it a lot more than psychologists do. But it has some limitations. One of them is that most theories in psychology only make ordinal predictions. So if you want to make a mathematical model out of some prediction, well, men are going to be less than women, or tall people will be more of than short people, or Canadians will be colder than Americans. Those are ordinal predictions. This is going to be greater than or less than that. And to try to turn those into equations and estimate all kinds of parameters becomes a bit of a dog job. But most data collected in psychology only have ordinal properties, or at best ordered metric. Ordered metric are the properties where not only do you know the orders of things, but you know the orders of differences between things. And then there are high order metrics and so forth. There's more than just the four different levels of measurement. And another thing, certainly most goodness of fit tests employ aggregated data, as in I ran 500 subjects, took an average, that's what it looks like, and here's my model that tries to do it. Under the often mistaken assumptions that all participants are using the same basic process, they're just varying in their parameter settings, which is very often false. Right, here's a little mental exercise. I'm going to give you a very quick mental exercise that I hope will confound you when you think about using the general linear model. Suppose we do the following experiment. I bring you into my lab and I say, I want you to predict whether the probability that Mary will go to church on a particular Sunday. So this is Sunday. What I'm going to do is to give you the history of Mary's church-going behavior over the past, let's say, 8 weeks. And I'm going to give you all kinds of combinations of those. I'll explain that in a minute. And for each combination, I want you to predict what's the probability that Mary is going to church. Now think of your prediction being right here. Okay, you're going to write it like from 0% to 100%. And here's Mary 8 weeks ago, 7 weeks ago, 6 weeks ago, 5 weeks ago. Got the idea? Okay. So we have Mary went to church, 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 went to church. Is that 8? Boom, you have to predict. So they're all gone to church. A pretty high probability you'll put down Mary went to church. How about didn't go to church, went to church, went. Probably pretty high probability. Didn't go to church, went. And you do all possible 2 to the 8th combinations. It gets really boring, but you got yourself a factorial design. Right? Are you with me? Okay, close enough. All right, go do a 2 by 2 by 2 by 2 by 2 8 factorial design analysis of variance. And here's what you'll find. Every main effect is significant. Every second order interaction is significant. Every third order interaction is significant. All the way up to the 8th order interaction. They're all statistically significant. Now I ask you, what was Mary doing to generate her predictions? And what would you be doing? Well, the answer, as it turns out, is quite clear. You'll look for patterns. How about this? Went, absent. Went, absent. Went, absent. Went. Thank you. How about this? Went, absent. Went, absent. Went. Okay. So you're picking up patterns, right? And you're using about 16 different pattern recognition processes to do that in your head. Okay? And we're averaging across all of those to produce a general linear model thing that says all main effects and interactions are significant. It doesn't tell you beans about what's going on in a person's head. It's a great problem in research. research and human decision making. Here's what the world needs. Right? Wouldn't it be nice, okay, if we had a simple means to evaluate the fit between ordinal predictions, not point predictions, and ordinal properties of observations, such as men will score lower than women, scores will improve with practice, that's a predicted order more quickly, sooner than later, as a predicted order of differences. Stress will be higher on Mondays and Fridays than on Tuesdays and Thursdays, will be lowest on Wednesdays. And that's something about time series. That's a semi-order because it doesn't make predictions about all possible orders. Wouldn't it be nice that we have a way that we could test prediction observation fit with both individuals and aggregates, as with one person at a time, or if you want to average over them, we could try that too. And it's simple, it's easily calculated and interpretable indices of fit, so you get numbers out that you can look at and say, wow, instead of saying, that accounted for 21% of the variance. Anybody know what that means? Yeah, if you square the deviations, I don't like to square my deviants, I like them raw. And you can aggregate them across people, and you can aggregate them across studies, if you want to do meta-analyses and so forth. So that's the dream. Now the question is, can we ever come up with something that fulfills that dream? And until 1975, I thought the answer was no. And then I started listening to the radio. History. If you are able, probably can't hear, if you're able to tune in to CBC, Canadian Broadcasting Corporation, 6:30 every night, it's been going for 40 some odd years. You'll hear a radio show that goes for an hour now called As It Happens. Wonderful, wonderful show where they telephone people in the news, like bank robbers who are holding up hostages in a bank. CBC phones them up. Hi, you're the bank robber? Yes, I am. You're holding some hostages? Yeah, there are 14 of them here. Well, so why are you doing this? This is where the money is. Okay, so it started in 1968, and one of the first hosts they had was this woman here. Unfortunately died of cancer at age 52. Her name was Barbara Frum, and she had one ignoble and one noble, I guess, credit to her life. One ignoble one is that she's the mother of David Frum, who was a speechwriter for George Bush for many years. But she was also a fabulous interviewer, just fabulous interviewer, wonderful person. During the time that she was had the show, before she had to leave it, the people who produced the show would end the show every night with some kind of lighthearted interview with somebody on the telephone. And they found a great source of lighthearted interviews by dipping into the pool of beloved British eccentrics. Hi, yes, I have 4,000 species of butterflies that I feed to my cats. A lot of British love that eccentrics. Okay, now, one night, 1975, I was sitting in winter, it was cold in Edmonton, and I was listening to the last of the show, and they put on this guy named Dennis Parsons, who had just published that book, The Directory of Tunes and Musical Themes, by Dennis Parsons. He was an employee at the British Library. He helped with publicity there. He was a press officer. He was born in 1914. I tried to find a photograph of him on the internet, but couldn't. I tried to find out if he's still alive. He'd be 101 by now. There was no death notice that I could find. I apologize for that. In that 10 minutes, it was one of the, I hope you've had these experiences or will have them in your career. The eureka moments, when bang, the penny drops. Oh my God, it was such an exciting idea. So I owe it to Barbara Frum and Dennis Parsons for putting me onto it. What did he do? He created this book. I should have brought some examples. If you open up that book, there's a little introductory comment stuff. And then there's just page after page of code. Okay, and he codes musical tunes. And they're coded with letters. U for up, D for down, R for repeat. And I'll show you what that means in a minute. why is this pretty eccentric? What is it? Oh dear, hello Barbara. It's nice to meet you. Well, you have this directory of tunes. Yes, yes. Well, why did you do it? Oh, I'm one of these folks who really enjoys singing things, but very often I can't remember the name of the tune. So, as I was walking to work, now I took the, remember 3x5 cards, index cards? I'd take them back in, I'd think of a tune, and then I'd write something down about it. And it was a code I developed myself. And I did this for many years. And you know, I had this code, I coded the first 16 notes, and I discovered that none of the codes repeated themselves. How does it work? Ah, he says, I do this. I start out with a note. Okay? And the first note of a tune that I can remember, then I sing the second note. And I ask myself, is the second note going up, down, or is it a repeat of the first note? If it goes up, I write down a U. If it goes down, I write down a D. If it goes repeat, I write down an R. Higher, lower, the second. And she said, oh, why do you do this? He said, well then, after I have that code, I can go find out what the name of the tune is, and then I write that down next to the code. So then anyone who wants to sing along the tune can sing it, write down their own code, look in my dictionary, directory, and find out the name of that tune. Well, how many tunes have you coded? Over 14,000, he said. And sure enough, you can sing along if you want. Consider, well, you don't know, Canada. Oh, Canada, home and native land. I don't sing, but it doesn't matter, because all we need to know are the ordinal properties. So occasionally you might hear that at a hockey game. Oh, now, that's up. That's a repeat. Down, up, down. True patriot love. You got the idea? Right, so, let's see. God, I can't remember. What's the American anthem? Oh, say. So, okay. Named after the guy who burned down the flag in the Canadian, it was a Mohawk Indian, I think. Anyway, War of 1812, I think. Let's see. Oh, say, can you see? You got the idea? You, dee. Oh, to joy, da 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 da. Are you are dee, and so forth. So those are 3 to 14,000 they put down in his book. Published the book. That was the end of the interview. And it just struck me. Oh my God, this is like. I'm singing a song, I'm providing data, in this case sequential data, and then I'm asking which of 14,000 theories, or predictions from theories, we'll call them, best match the data. Got the idea? So there are ordinal properties of what I'm singing, even if I'm singing off key, and there are these 14,000 predictions. And what do you do in his directory? I should have bought my prized copy, but I was afraid it would be confiscated by some literate customs official. And it's all alphabetical. It goes from the D to U. At the end. So you just go through the page until you find the perfect match. Now, for Dennis Parsons, who worked at the British Library and was not a mathematician, he wanted the exact match, and it's pretty easy to get, or very close to it. But then, let's just try taking that idea and extending it a little more. Now, what Dennis Parsons did was to look at adjacent notes, but of course we can look at non-adjacent notes as well, and by doing so, can even be more specific in our predictions. Is the first and the third note, the third note higher than the first, and the second note higher than the fifth, or fourth, or 27th, We can also look at distances between notes, distances between data, and start coding the order of distances that way. Okay? And And we don't have to rely on exact matches. Can't we create a very simple index of just how close the ordinal match is between the prediction and the observation? Is it 100% of the notes? Let's call that 1.0. Is it 0% of the notes? Let's call that 0.0. Is it somewhere in between? Okay? So then I started thinking, wait a minute. We can use this as a statistical procedure for finding out how well our ordinal predictions, which is almost all we have in psychology, match the ordinal properties of whatever data we collect. Okay? Okay? And it's really simple. I'm sorry, I'm not a mathematician. I can't do calculus. I got a C+. But because of great inflation, I'm sure it'd be an A+ like that. So, I have to apologize because this is so easy. What do? You gather at least two measures. Like how long is your left foot and how long is your right foot? Okay? That's two measures, okay, you got two numbers. Measurement, remember, is the assignment of an observation to a number. How many people know the definition of a statistic? What have you heard? Either way. What's a statistic?
It's a sample estimate of a parameter.
Yeah, okay, that's Here's the definition I learned. It's a number that represents some aspect of two or more other numbers. So, which I think is the best definition of all. Here's a 27, here's a 32. Right? You want a statistic? Okay, 27. What's that? That's the lowest. Okay? 32, what's that? Oh, that's the maximum. Whatever the thing in this middle, that's the mean. How about the two numbers added together divided by 41? That's another statistic. It's meaningless. Okay. So I gather these two measures. And these two measures might be relevant to somebody making an ordinal prediction, like your left foot will be longer than your right foot. That's order. Longer than, greater than, less than, so forth. And then you see, does it match in your observations? And if you have lots of observations, you just count how many times does it match and how many times does it mismatch. And it gives you an index of the goodness of ordinal fit. That's an evidential statistic. An index of the evidence you have for or against a particular hypothesis. Notice I'm not talking about samples going to distributions. I'm saying if you have a hypothesis, does it generalize to your observations? And if so, how much? And if you want more generality, go get more observations, for God's sake. So, in a way, it's going to be like Kendall's Tau. My favorite statistician was Maurice Kendall, who wrote the obituary of Sir Ronald Fisher. He said, although he could be gratuitously rude, and often was. Okay, so what do you do? So, I'm going to give you some examples here after the break. Okay, so what do? Every time you say, I think that's going to be greater than that, and you happen, well, let's call it a hit. And if I think that that's going to be greater than that, and the reverse happens, or it doesn't happen, you call it a miss. It's easy so far, you following me? Don't square anything yet. We'll plug this into SPSS. And if you have a tie, I think my left foot is going to be longer than my right foot. Oh, actually, they're equal. Well, as you may know, in non-parametric statistics, you have a lot of ordinal statistics. There's this big debate about what to do with ties. And the debate goes, you ignore them, or you count them as a miss, because if you're predicting strong order, like greater than, but not greater than, equal to, okay? And it's not greater than, it's equal, so it's a miss. Versus people say, well, we'll just predict greater than or equal to, blah, blah, blah. I just say ignore them. And also if you have missing data, well, you don't have it, so you just ignore that. Don't try to fill in the blanks. Just don't count it. It's really easy. So you ignore ties, you ignore missing data in general, and then you just calculate an index that might seem psychologically meaningful to you. One of them is the proportional probability of hits that you get. So you want to know the number of hits, you want to know the number of misses. And you can say, so how many of the total number are hits? It goes from 0 to 1. Or if you like something that it's the mathematical equivalent under certain assumptions of Kendall's Tau, I call it an index of observed fit. Number of hits minus number of misses divided by the number of hits plus the number of misses, which is, if you have complete data set, that's Kendall's Tau. And then you save the number of hits and the number of misses for the future. And you report those too, because if somebody else does an experiment on something else, that's testing the same hypothesis, they can add your numbers to their numbers. Because when you're trying to sample in order to test a theory, as long as the theory doesn't have scope conditions that says, no, it doesn't work there, you can test it anywhere and on anything. You get theories about how stars are born, but it only works on stars that are randomly sampled. Oh, shut up. It doesn't say it only works on stars. And test it on anything you want. You don't have to worry that much about random samples. You do if you want to generalize in the sample population, but not if you want to test whether the theory will generalize to your observations. Example 1. Can we go through this example and we'll take a break? Or do you want to, oh no, it's close to a break now. Yeah, that's good. No? Okay, well, I just made these up, and the problem is, those of us who teach, I hope long ago, but not me, learned that you make or break a lecture by your examples. Because people remember the examples and reproduce the general ideas from that. I don't know if these are good or not, but here we go. Suppose you have a theory, and being in psychology, it would be a very weak, loose, sloppy theory. The more neural connections we have in our brain, the more irony we perceive in the world. Does that make sense? Neural connections increase with age. I hope. Well, some of us are in decline. That's another story. Ergo, people more frequently detect irony as they age. So the older they get, the more irony they see. Now, suppose somebody invented the standardized international irony test. There could be one. How many tests does the Metal Measurements Yearbook now have? There's a thing called the Metal Measurements Yearbook that's about as thick as an old phone book. It used to have 4,000 psychological tests. You think, look at the combinations, look at the PhDs that come out of that. I'm going to select one from page 23, I'm going to select one from page 114, and I'm going to correlate them. Okay, so let's say we want to test this. Now notice the theory is said, but it only works on women, or it only works on Iranians, so we can test it anywhere. Let's test it on Fred to see how well Fred, sense of irony in that. And let's just say that we give Fred the irony questionnaire, that's the IQ, in the following years of age. So we capture Fred while he's 10, we fill out our IRBs, is that what they're called? Something like that. And we get the parents' permission, and so he takes it at age 10, age 15, 22, and so forth. Okay, at those different ages. And we score the irony questionnaire, and let's say it goes out of 100. So irony can be 0. What do you mean by irony? All this irony of everything you said. So we think, what does that theory predict? Well, the theory presumably would predict that at A15 there's going to be a higher score than an A10. That's how. You with me? And also predict that at A10 you're going to have a lower score than an A22. And at A10 you're going to have a lower score than an A25. Okay? We won't go all through all of these because it gets real boring. 15 and 22, and all the way up to, at age 32, there'll be a lower irony score than at age 49. So that's called the predicted ordered pairs, or the POP set of predicted ordered pairs. Now, in this particular case, we're making predictions about all possible pairs of these numbers. In lots of other conditions, we don't make predictions about all of them. We have a smaller set, and that leads us to the idea of the scope of the theory. I'll talk about that as we go on. Okay, so just working for this one. there are the results, which of course I made up. Fred doesn't even exist. But I didn't need ethics clearance for this. Okay, so let's say those are the scores. So what do we want to do, okay, following the tradition of Dennis Parsons and his musical tunes, to find out how well do the predictions of that theory match the observations? Now, according to the predictions in this very simple case, the numbers should get bigger as they go down the column. So that should be, according to theory, smaller than that one, and those two should be smaller than that one, and those two should be smaller than that one, and so they should go up. You don't have to sing for this one, but are you ready for the count? Is A15 greater than 10? No. So stick out your hand and hold out your thumb. That's one miss over your left hand. Okay? Does A10, is the A10 smaller than A22? Yes. And that's one hit. So we have 1 and 1 so far. Is A10 smaller than A31? Oh, sorry. Got your fingers out there still? So, we simply count, under the fingers, and this is digital. Or if you want, you can, 1, and put it in an R program, 2, and be more scientific. So, that's all you do. You go through it, you count up the number of hits, and you count up the number of misses. Okay? So, in this, I did it for you. 12 hits, 2 misses, 1 tie, and oh, there's zeros. Oh, right. Very good. I know what she was. But anyway, got the idea? Okay. So then, what's the probability of a hit? The proportion of hits. 12 over 12 plus 2. Can you do that? Little calculators will do that. Costs 49 cents. Or the index of fit, you can even do this. 12 minus 2 divided by 12 plus 2. That's like a Kendall's tau. And it looks kind of like a correlation coefficient, but it's not scalable the same way. You get the idea. So what does that mean? That means if you walked in with this theory, or if you walked in without the theory, and we're trying to predict some ordered relation in those different ages of Frank's irony scores, and we're blind to a theory, and just flip the coin and make a prediction. Okay? Chances are about 50% that you'd be right. With the theory, you've increased it from 50% to 86%. That's what it means. It's the proportion of times you got it right, you got a hit. Okay? So how much does the theory generalize to Frank? 86. You think, yeah, I can't trust it because it's too simple. I might square something pretty soon. Then I will argue, in fact, it's funny, the most recent publication I have of this is in a funny journal you've never seen, I'm sure. It's called the Journal of Artificial Societies and Social Simulation. Freudian slip. JASSS. It comes out of the University of Surrey, and it's been going for a long time. A few years ago, it was published. I had a whole section on statistical significance of this, for those who want that sort of thing. And I was told by the editors to take it out. So, if you like computer simulation, there's a place that you can go, you don't have to do it. So, can you, if you ask, yeah, but is that significant? The answer is, well, actually, we can tell. Okay? Well, one way, because I make all predictions, is to just go up and look at Kendall's tau, because that's Kendall's tau right there, because we've made predictions about all kinds of things and never know tau. There's only one time, it's good enough. But in other cases, you can just rely on resampling and bootstrap. How many people know about resampling and bootstrap? Okay, a lot of you do. So read about that, that's great. It's computer-intensive stuff. Really making a huge difference in statistics these days. Okay, now, there it is. We just did an analysis of Frank. Now that's not an awful lot of data, you might think. Well, I don't know whether to trust the theory or not. It seems to work pretty well on Frank. Maybe it doesn't work on other people. And what does a scientist say to that? Go get some other people. Yeah? And pretty soon you may get 10 people or 100 people. And you do individual analyses on each one. You analyze before you aggregate. And maybe after that you discover something like this. You know, I've tested it now on 100 people, 50 men and 50 women. And I find that I get positive scores for 49 of the 50 women and 1 negative score, meaning I do worse with the theory than, from an IOF than I did if I just guessed by chance. But for men, I only get positive scores for 13 out of the 50, not 49 out of the 50. And that would even, well, if you want to say, oh, let's do chi-square. And if you want to be traditional about it, or some other thing, you use as the dependent variable the goodness of fit index for each of these people. But you've analyzed the people individually over time. And indeed, one of the things that happens with this is it's really good for analyzing what happens to individuals over time. You don't worry about are those independent observations? Of course not. But that's the pattern that was given by whatever process happened to be going on in Frank's head. You don't care what generates the pattern, you just want to ask, does your theory match the pattern? And then if it does pretty well, you think, well, that's still, we can't eliminate that. Yeah, that's one possibility. Is that making sense? Does anybody have questions? And then you're thinking, yeah, but we've only used our fingers. We haven't gone to SPSS yet. I'm sorry. Okay, what's next? You want to go through one more? I'll probably end early because I don't have enough. I think I have this one and maybe one more. But one of them is on baby names. Do you know the huge database in the United States on baby names? Popularity of baby names. Oh, it's fascinating. So that's a good part. So put your head down now. We'll come back. Okay, let's try one more and then we'll have a break. Okay, example 2. I made this up.
That's what you said last time. Didn't you say that a few minutes ago that was the last one?
Oh, I probably did. I can't remember. It's my age. Okay. Okay, here's another silly example, but maybe a similar point. Just a little more complex than the first one. This is why I call the no-name brand resilience theory. Is resilience still a hot topic in psychology these days? It'll be gone in a couple of years. Okay. Depression is highest immediately following a tragedy, then steadily declines. Now, how we came to derive that is a mystery to me. I just made it up. So a little bird told me at night that this could happen. What are the psychological mechanisms? I don't know. Decline is more likely to happen for women than for men. Decline is more likely to happen for younger people than for older people. Okay, so it sounds as though we got a nested kind of a model. Is that what they call it these days? Hierarchical, blah, blah, blah. Yeah? Okay, so here's a little bit more data. So here we have a sample of 4 females, F1 through F4, 4 males, with the appropriate letters in front. We have their ages, and we have their depression scores on the Beck? I don't know. Do you know Aaron Beck is still alive? He's 94 years old. Amazing guy. He had the Beck depression inventory, for those who don't know. Okay, so somehow we get measures of whatever questionnaire this is. It's scored from 0 to 10. 0, I'm not at all depressed. To 10, I'm suicidal. And here are the digits that we get out, but there are a couple of missing ones, perhaps because these people are so depressed they didn't have motivation to fill it out. F2 has 2 not availables, and M4 has 1 not available. Doesn't matter. It's really easy. So what do we do with this? What would you do typically if you were putting this through SPSS? For one thing, try to estimate these missing values. That's probably one thing you do when you argue over algorithms. And then you want to get averages, right? And you want to sort of do kind of a one-way analysis of variance, repeated measures design, hoping that the variance covariance matrix is blah, 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 blah. You know all that stuff? Don't worry about it. This is the sloppy method that gets the job done as well. First thing, you can, if you want, look at the predicted orders, which we'll talk about in a minute, and compare them to the averages, and you might as well, it's kind of fun. But you can also do it person by person. And we end up with 8 different measures of goodness of fit for 8 different people. And I'll argue that that's somehow a bit more meaningful. Lots of ways. Okay, so let's go back to the hypothesis. Depression is highest immediately following a tragedy, then steadily declines. Let's start out with that one. That means that in day 2, that's day 1 after some tragedy, and we'll talk about that in a minute, you're going to get a higher depression score than on day 2. Day 1 is going to be higher than day 3, day 4, and day 5. Complete set of predictions. Pretty simple. So once I have that complete set, let me say, I went through and did the counting for you, and I say, okay, for female, 1, she's age 19, ended up with 8 hits. 8 out of the 10 possible combinations made a correct prediction. There was 1 miss and there was 1 tie. Let's just go back and see what the tie was. So day 2 and day 3. We're going to ignore it, but we write it down anyway. And she had 0 not availables. And if you do the math, it comes out that the index of observed fit is plus 0.78. 78% better than chance is a sloppy misinterpretation, but you get the idea. Now I go and do it for female 2. Okay? There are 2 hits, 1 miss, and 7 not available, so we don't get much data for female 2. What little we do have show that 2 out of the 3 times you're getting hit. And we continue on for each one of these to get these iOS scores. But the really, I think, better one to do, we'll use those in just a minute, but the better one to do is to say, here are the females and here are the males. For females, if you talk about that, 8 and the 2 and the 4 and the 1, you get 15. For males, the 8 and the 5 and the 2 and the 0, and you get 15 as well. That's where that comes from. So, and because, remember that decline is more likely to happen for women than for men, which presumably would translate, loosely speaking, into you get higher indexes of observed fit for women than you do for men. And decline is more likely to happen for young people than for older people. You'll get higher indexes of observed fit for the older people than the younger, however you want to define that. So here we have females and males, okay, so females here, okay, if we aggregate across all of them, females here do barely better than, the theory does barely better than chance, and for males it does better, does approximately 0. All doesn't happen there. For age, less than 30 years old, I just did a median split, you don't have to, you can define age however you want, because the theory isn't saying less than 30 or greater 30, so it's up to you. Less than 30 years, okay, the overall index of fit for all 8 people was plus 0.7. Greater than 30 years, the overall index was minus 0.58. So I look at that and I said, oh, there's something there. So it seems as though the relationship, if you look at these, you say, and this is how I would imagine dear William Estes would say, that's a pretty good fit, that's not, that's not, that's a pretty good fit, that's a pretty good misfit, that's a pretty good fit, that's a pretty good fit, that's a pretty good misfit, that's a complete misfit. So we might go down here and say, what proportion of the people have approximately good fits? I'd say 1, 2, that's all. How many? So that's 2 out of 8. How many are doing negative direction? 1, 2, 3, 4. Okay? 4 out of 50% of them. 4 out of 8. And probably I want to keep that head count 4 out of 8 and 5 out of 8, and here they're how they're coded for females who are young, females who are old. And they got some numbers, and then I put those in some data depository, and then perhaps 2 years later, some undergraduate somewhere does the same kind of study, but maybe using a different measure of depression, a different sample of people, doesn't matter because the theory isn't stating what it's supposed to be, and then takes the numbers that she or he got in her or his study and adds them to some database, and over time we start collecting frequency counts of all of these with appropriate information about the people who were scored, and we start building up a picture of how well this particular theory does. Does that make sense? I'm sorry, other than that, I'll show you more complex examples after the break, but that's sort of it. Right? Fingers, little tally notes if you want, count them up, and that's how it works. But I find that, particularly in the kind of stuff I do now, it's actually quite useful for looking at individuals when we have data, when we collect data about individuals in various situations over time. It's nice for trying to promote more theories, people to come up with some hypotheses, but we don't need to have them. And one of the things I'll show after the break is how you can take a data set like this and ask yourself, what's the best possible score any theory could get looking at modal responses or pairs. And sometimes that can be very instructive too, to say, should I throw out this data set because it doesn't show us anything, or should I keep it for further stuff? I'm really sick of hearing myself. Can we take a break? We'll come back. Thank you.